In our previous module 2, we have seen about the qualitative behavior of the system of differential equations. We have stated theorem where we have shown that if both the eigenvalues are real and negative, then we get a stable node. In this module 3, we will look into the proof of this theorem. Paths of the linear system. Here we consider the linear system of the form dx dt is equal to ax plus by and dy dt is equal to cx plus dy given by equation 1, where a, b, c, d are the real constants. Here 0, 0 is clearly the critical point of the linear system 1, and we assume that determinant a, b, c, d is not equal to 0, and hence 0, 0 is the only critical point of 1. The characteristic equation of 1 is obtained from the equation determinant of a minus lambda I is equal to 0, and if you do that, you will get determinant a minus lambda b c d minus lambda is equal to 0, and if you expand that, you will get the characteristic equation as lambda square minus a plus d into lambda plus ad minus bc equal to 0 given by equation 2. Previously, we have seen that if the characteristic equation given by 2 are real and negative, then we get a stable node. Here we will prove mathematically that actually we will get a stable node. So, the hypothesis is that if the roots lambda 1 and lambda 2 of the characteristic equation 2 are real, unequal and of the same sign, then we conclude that the critical point 0, 0 of the linear system 1 is a node. We assume that lambda 1 and lambda 2 are both negative, and we take lambda 1 less than lambda 2 less than 0. Now, the general solution of the linear system 1 may be written as x equal to c1 a1 e to the power lambda 1 t plus c2 a2 e to the power lambda 2 t, and y equal to c1 b1 e to the power lambda 1 t plus c2 b2 e to the power lambda 2 t, where a1 b1 and a2 b2 are definite constants provided a1 b2 is not equal to a2 b1 and c1 and c2 are arbitrary constants. Now, if we choose c2 equal to 0 and substitute it in equation number 3, we will get x equal to c1 a1 e to the power lambda 1 t and y equal to c1 b1 e to the power lambda 1 t, which we name as equation 4. Similarly, choosing c1 equal to 0, we will obtain x equal to c2 b2 e to the power lambda 2 t, y equal to c2 b2 e to the power lambda 2 t given by equation 5. Now, for any c1 positive, the solution 4 represents a path consists of half of the line b1x is equal to a1y of the slope b1 by a1. The meaning of this is, here if we divide this, we will be getting x by y, this c1 and this c1 will cancel, and e to the power lambda 1 t e to the power lambda 1 t will cancel, and you will be getting y by x is equal to b1 by c1. This is exactly shown here, that is, for any c1 positive, the solutions 4 will represent a path consisting of half of the line b1x is equal to a1 by with slope b1 by a1. and for C1 less than 0, the solution 4 represent a path consisting of the other half of the line. And since lambda 1 is less than 0, both these half line paths approaches 0 0 as t tends to plus infinity. And since by x is equal to b1 by a1, these two paths enter 0 0 with slope b1 by a1. Now, if you look into the figure, you consider any one of these straight line, say this one. So, the first part says that if C1 is greater than 0, the solution represents a path consist of half of the line b1x equal to a1y, and let that half be this much, this half of the line. And if C1 is less than 0, the solution represents the other half. So, considering both C1 greater than 0 and C1 less than 0, we will get this full straight line. And since the straight line is of the form y equal to b1 by a1x, that is y equal to mx, where m the slope is b1 by a1, and we all know that it represents a straight line passing through the origin, and hence these two straight line will enter the origin with slope b1 by a1. In the similar manner, for any C2 greater than 0, the solution 5 represents a path consist of half of the line b2x is equal to a2y, while for any C2 less than 0, the path so represented consists of the other half of this line. And these two half line paths also approach 0 0 as t tends to plus infinity and enters it with a slope b2 by a2. This means, if we again consider this figure, that if we consider this as the line b2x is equal to a2y, then for C2 positive, let it represent this particular straight line, and for C2 negative, it represents this particular straight line, and both of them are approaching 0 0 in this direction. And since it is a straight line passing through the origin, both these half lines will enter the point 0 0. Thus, the solutions 4 and 5, it provides us with 4 half line paths which approaches and enters 0 0 as t tends to plus infinity. Now, let us consider the case when neither C1 nor C2 is equal to 0, that is C1 not equal to 0 and C2 not equal to 0. And then the general solution 3 represents a non-rectilinear paths. We have already assumed that lambda 1 is less than lambda 2 is less than 0, and all these paths will approach 0 0 as t tends to plus infinity. Further, if we calculate this ratio y by x, which is equal to C1 b1 e to the power lambda 1 t plus C2 b2 e to the power lambda 2 t divided by C1 a1 e to the power lambda 1 t plus C2 a2 e to the power lambda 2 t. If we take common C2 b2 e to the power lambda 2 t, we will be getting C1 b1 by C2 e to the power lambda 1 minus lambda 2 into t, and likewise the denominator. As t tends to infinity, we can see lambda 1 minus lambda 2 is less than 0, and this whole term will tend to 0. This term also tends to 0 as t tends to plus infinity, and hence we will have limit t tends to plus infinity y by x is equal to b2 by a2. And so, by definition, these paths will enter 0 0 with a limiting slope b2 by a2. and hence we get that if both the roots lambda 1 and lambda 2 are real, unequal and less than 0, then the given system will represent a node at the origin, and in this case it is a stable node. Thus, we conclude that all the paths, both rectilinear and non-rectilinear, they enter 0 0 as t tends to plus infinity, and all except two rectilinear ones enter with slope b2 by a2, and according to the definition, the critical point is a node and clearly it is asymptotically stable. Now, if lambda 1 and lambda 2 are both positive and we take lambda 1 greater than lambda 2 greater than 0, we see that the general solution of 1 is still in the form 3, and the particular solution of the form 4 and 5 still exist. The situation is same as before, except all the paths approach and enter 0 0 as t tends to minus infinity. The critical point 0 0 is still a node, but it is in this case it is unstable. And please note, since the node is unstable, all the arrows here are moving away from the origin. In our second theorem, our hypothesis is that the roots lambda 1 and lambda 2 of the characteristic equation 2 are real, unequal and of the opposite sign. The critical points in this case is a saddle point, and since they are of opposite sign, we assume that let lambda 1 is less than 0 and lambda 2 is greater than 0. Our general solution of 1 is taken as x is equal to c1 a1 e to the power lambda 1 t plus c2 a2 e to the power lambda 2 t, and y equal to c1 b1 e to the power lambda 1 t plus c2 b2 e to the power lambda 2 t. And the particular solutions are of the form 4 and 5, which is x equal to c1 a1 e to the power lambda 1 t, y equal to c1 b1 e to the power lambda 1 t, which is obtained by putting c2 equal to 0, and when we put c1 equal to 0, we will get x is equal to c2 a2 e to the power lambda 2 t, y equal to c2 b2 e to the power lambda 2 t. Here a1 b1 a2 b2 are definite constants and c1 and c2 are arbitrary constants. So, like before, if c1 is greater than 0, the solution 4 represents a path consisting of half of the line b1x is equal to a1 by, while for c1 less than 0, they will again represent a path consist of the other half of the line. So, in this case, since lambda 1 is negative, we will get this as a half of the line which is approaching the point 0 0, and this as another half of the line which is again approaching 0 0. So, since lambda 1 is negative, both these half lines approach 0 0 and enter 0 0 as t tends to plus infinity. Now, for any c2 positive, the solution 5 represents a path consist of half of the line b2x equal to a2y, while for any c2 less than 0, the path represents consist of other half of this line. But since in this case lambda 2 is greater than 0, both of these half line paths now approach and enter 0 0 as t tends to minus infinity, and hence in this case we will get this straight line where it is moving away from the origin. And if c1 not equal to 0 and c2 not equal to 0, the general solution 3 represents a non-rectilinear paths, and since lambda 1 is less than 0 and lambda 2 is greater than 0, none of these paths can approach 0 as t tends to plus infinity or as t tends to minus infinity. Moreover, none of them pass through 0 for any t0 such that minus infinity less than t0 less than infinity. As t tends to plus infinity, we see from 3 that each of these non-rectilinear paths becomes asymptotic to one of the half-line paths defined by 5, and as t tends to minus infinity, each of them becomes asymptotic to one of the paths defined by 4. Therefore, there are two half-line paths which approach and enter 0 as t tends to plus infinity, and two half-line paths which approach and enter 0 as t tends to minus infinity. All other paths are non-rectilinear paths which do not approach 0 as t tends to plus infinity or as t tends to minus infinity, but it will become asymptotic to one or another of the 4 half-line paths as t tends to plus infinity or as t tends to minus infinity. And hence, by definition, the critical point 0 is a saddle point, and clearly it is unstable. We have just looked into the system of linear equations, where we have taken two linear equations and we have proved that if the roots are real and negative, then it will represent a node. We will now look into the generalized system of linear equations and look into its stability. Here we consider the stability question for the solution of autonomous differential equation. Let x equal to phi t be a solution of the autonomous differential equation of the form x dot, which is dx dt equal to fx, given by equation 6. We are interested in determining whether phi t is a stable or unstable solution. That is, whether every solution psi t of 6 which starts sufficiently close to phi t at t equal to t0 must remain close to phi t for all future time t greater or equal to t0. Now, the definition: the solution x equal to phi t of 6 is stable if every solution psi t of 6 which starts sufficiently close to phi t at t equal to 0 must remain close to phi t for all future time t. In mathematical terms, the solution x equal to phi t of 6 is stable if for every epsilon positive there exists a delta which depends on epsilon such that norm of psi j t minus phi j t is less than epsilon if norm of phi j t0 minus psi j t0 is less than delta, which is a function of epsilon j equal to 1 to dot dot n for every solution psi t of 6. The stability issue can be completely resolved for linear autonomous differential equation, and the following theorem gives the complete information. Every solution x equal to phi t of x dot equal to a x is stable if all the eigenvalues of A have negative real part. Every solution x equal to phi t of x dot equal to a x is unstable if at least one eigenvalue of A has positive real part. And the third one, suppose that all the eigenvalues of A have real part less or equal to 0 and lambda 1 equal to I sigma 1 dot dot lambda L equal to I sigma L have non-zero real part. Let lambda j is equal to I sigma j have multiplicity k j, that is, the characteristic polynomial of A can be factored into the form p lambda is equal to lambda minus I sigma 1 to the power k 1 lambda minus I sigma L to the power k L q lambda, where all the roots of q lambda have negative real part. Then every solution x equal to phi t of 6 is stable if k has k j linearly independent eigenvectors for each eigenvalue lambda j equal to I sigma j. Otherwise, every solution phi t is unstable. The proof of the first part: we know that every solution x dot is equal to A x can be written in the form psi t is equal to e to the power a t psi 0. Let phi I j t be the I jth element of the matrix e to the power a t, and let phi 1 0, phi 2 0 psi n 0 be the components of psi 0. Then the ith component of psi is psi I t is equal to phi I 1 t psi 1 0 plus plus phi I n t psi n 0, which is equivalent to summation j equal to 1 to n phi I j t psi j 0 given by equation 7. Now, let all the eigenvalues of A have negative real part, and let minus alpha 1 be the largest of the real part of the eigenvalues of A. It is easy to show that for every number minus alpha with minus alpha 1 less than minus alpha less than 0, we can find a number capital K such that mod of phi I j t is less or equal to k times e to the power minus alpha t, where t is greater or equal to 0. Consequently, mod of psi I t is less or equal to summation j equal to 1 to n k e to the power minus alpha t mod of psi j 0, which is equal to k e to the power minus alpha t summation j equal to 1 to n mod of psi j 0 for some positive constants k and alpha. Now, mod of psi j 0 is less or equal to norm of psi 0, and hence norm of psi I t is equal to maximum of mod of psi 1 t mod of psi 2 t mod of psi n t, which is less or equal to n k e to the power minus alpha t norm of psi 0. Let epsilon greater than 0 be given, and we choose delta equal to epsilon divided by n k. Then norm of psi I t is less or equal to epsilon if norm of psi 0 is less than delta and t greater or equal to 0. Since norm of psi I t is less or equal to n k e to the power minus alpha t norm of psi 0, which is less than n k epsilon divided by n k equal to epsilon. Thus, the equilibrium solution x t equal to 0 is stable. For the second part of the proof, let lambda be an eigenvalue of A with positive real part, and let V be an eigenvector of A with eigenvalue lambda. Then psi t is equal to C e to the power lambda t V is a solution of x dot equal to A x for any constant C. If lambda is real, then V is also real, and norm of psi t is equal to mod C e to the power lambda t norm of V. Clearly, norm of psi t tends to infinite as t tends to infinite for any arbitrary C not equal to 0. Therefore, x t equal to 0 is unstable. And if lambda equal to alpha plus I beta be complex, let V equal to V1 plus I V2 is also complex. In this case, e to the power alpha plus I beta t into V1 plus I V2 is equal to e to the power alpha t cos beta t plus I sin beta t V1 plus I V2, which can be written as e to the power alpha t V1 cos beta t minus V2 sin beta t plus I times V1 sin beta t plus V2 cos beta t is a complex valued solution of x dot equal to Ax. Therefore, psi 1 t is equal to c e to the power alpha t V1 cos beta t minus V2 sin beta t is a real valued solution of x dot equal to Ax. Clearly, if norm of psi 1 t is unbounded as t tends to infinity, if c and either V1 or V2 is non-zero, thus x t equal to 0 is unstable. And from the proof of C, if A has kj linearly independent eigenvectors for each eigenvalue lambda j equal to I sigma j of multiplicity kj, then we can find a constant k such that mod of e to the power at ij is less or equal to k. Therefore, norm of psi t is less or equal to nk norm of psi 0 for every solution phi t of x dot equal to Ax. Thus, from the proof of A, we have x t equal to 0 is stable. On the other hand, if A has fewer than kj linearly independent eigenvectors for all eigenvalue lambda j equal to I sigma j, then x dot equal to Ax has the solution psi t of the form psi t is equal to c e to the power I sigma j t v plus t times a minus I sigma j I into v, where a minus I sigma j I into v not equal to 0. If sigma j equal to 0, then psi t is equal to c v plus t a v is real valued. Moreover, norm of psi t is unbounded as t tends to infinite for any arbitrary c not equal to 0. Similarly, both the real and imaginary parts psi t are unbounded in magnitude for arbitrary small psi 0 not equal to 0 if sigma j not equal to 0, and therefore, the equilibrium solution x t equal to 0 is unstable. Now, definition 0.2, it gives a solution x equal to phi t of 6 is asymptotically stable if it is stable and if every solution psi t which starts sufficiently close to phi t must approach phi t as t tends to infinite. Now, let us consider an example where we have to check whether the system of the differential equation given by x dot or dx dt is equal to Ax, where A is minus 1 0 0, 0 minus 1 1 and 0 minus 1 minus 1 is stable, asymptotically stable or unstable. Now, we can easily find the eigenvalues of this coefficient matrix from the definition mod of A minus lambda I is equal to 0, and if you solve that, we will get lambda equal to minus 1 and lambda equal to minus 1 plus minus I. Since all the three eigenvalues have negative real part, therefore, every solution of this differential equation x dot equal to Ax is asymptotically stable. Summing up, in this module we have learned about the mathematical proofs of the linear system when the two roots of the eigenvalues are real and negative. In our next module 4, we will look into the generalized version of the autonomous system and learn about the stability, about the equilibrium points. Thank you.